everyone, welcome back. I'm Anna Ruth. Let's get another physics lab, lab 4, oscillations. So introduction, basically the purpose of this lab was to examine the motion of a string mass system where the mass is swinging and also oscillating, and then compare the observed model to a computational model and see if it follows the energy principle. And so I chose option 1, video analysis. So I input the given video into tracker, took the output, placed the values in the glow script. Some fundamental principles, Newton's second law, of course, force is mass times acceleration, also equal to the change in momentum over change in time, and F net in this case is the force of the spring plus the force of gravity. And then energy principle, the energy of the system is the work of the surroundings plus the heat, and we got delta K plus delta's potential energy of spring plus potential energy of gravity equals 0 because that's the energy of the system in this case. And then some more equations and position and velocity update as always. And we got the description of the experiment I described already. And the system was the spring mass system and the earth, and the surroundings were nothing. Initial conditions, we have mass, length of the spring, stretched, and R initial and V initial. This is what it kind of looked like on on tracker, sorry. We can see it's oscillating, it's moving in a circle, and the output kind of looks like what it did. And calculations, period of oscillation we found using this formula, and we found, T, and then we found the spring stiffness. And then we found the length of the relaxed spring. So this is the code. We plugged in the mass that was already given and the position, which was in the tracker data vector. The velocity was initial 0, starts at rest. We have gravity's 9.8, we got spring constant that we calculated, L naught that we calculated, and we have these different equations put into code form. Calculations, so this is basically the different forces, force of gravity, force of spring, F net we already know, F spring plus F grav, momentum principle, F equals ma, we updated the velocity, we updated the spring, and then we calculated the energy changes. So delta E, this is going to have to do with the energy principle. This was what the output kind of looked like. Very cool, very similar. These are some graphs. They are from the model and the experiment, so you can see there's not a lot of discrepancy. It's kind of wibbly wobbly more, but it's pretty similar. We get some discrepancy as you go further along. And yeah, so we approximated, or we assumed, that work done by the surroundings was 0, and the accuracy could be a little bit off because the center of mass might not be right for every frame, user error on tracker. And we have to ask ourselves, is the energy principle satisfied? Yes, because we see that delta E, colored orange right here, stays 0 the entire time. So energy is conserved and never lost, it's just transferred. So we can see that in this equation, delta K, so kinetic energy plus the potential energies of the spring and gravity, will equal to 0 because this is the energy principle basically, and it's satisfied in this occasion because you have, we ignored work on the surroundings, so get rid of that, but if we have delta E equals 0, then we can set all of this equal to 0. And it's displayed in the output from the computational model. And then we took the estimates, or we found the estimates of oscillating periods for each direction of the spring, because we were going to see if there was a change between like the stiffness values and the direction that they're going. And initially I didn't think that there'd be a difference, but when we actually do the calculations and do these estimations, we see that there are different spring stiffnesses. So that was an interesting takeaway. Thank you for listening. Have a good night or good morning.